And I make Bartek. Bartek, are you here?
Yes.
So I make you a co-host, but why is this not working? Let me stop sharing and then I will share again. Yeah. Why you make someone co-host? I have to go to participants. Make co-host. Bartek, you're gonna be co-host.
Sure. Okay.
Okay. All right. And we. All right. I'm going to start sharing. Okay. Okay. So I have to say, guys, if you want this to completely make sense, all of this, you kind of have to do some readings, and just relying on the notes will not do it. Yeah. So most of what I say comes from basically the Cabal volumes. The follow-based theorem. So I think it's in. I think it's probably in Paul Larson's book on AD+, but it's on the Cabal seminar. So 7.7, independence of AD. Like this DC from AD, I think. Independence of DC from AD. Okay, and let me remind you what the theorem is that we need. Right? So ADR, assume ADR. There is a fine, normal, ultrafilter. Well, they say normal, so of course countably complete ultrafilter. P omega 1 of R. Okay. Let me remind you what that is. So P omega 1 of R, this is set of sigma which are subsets of R, and the cardinality of sigma is countable. And then, so let's call this definition. P mu, suppose X is any set, right? I guess this is just true for any, suppose X is any set. And is an ultrafilter. I mean, P omega 1 X is the set of countable subsets of X, right? Okay, I just want to remind you what it means to say fine and normal. So fine. This is as always. So fine means sorry, for every fine means that for every A in X, the set of sigma in P omega 1 of X such that A belongs to sigma, that belongs to mu. And normality is what's a bit different because we don't have axiom of choice. So for every f, so for every f, which is a function from p omega 1 of r into p omega 1 of r, such that the set of sigma in p omega 1 of r, which have the property that f of sigma is a subset of sigma. So if you know the definition of supercompact, we usually then, when you talk about normality there, we say f of sigma is a member of sigma. But that's because your base set is well ordered, so you always pick the least element, right? So if this has measure 1, then yeah. So for every f such that this has measure 1, sorry. There is an A in X such that the set of sigma with the property that A belongs to f of sigma, right, is measure 1. Okay, so we have a large, think of Walsh's theorem if this is where it's mostly used, right? Trying to prove Walsh's theorem, there's going to f of sigma is going to be sort of possible witnesses to some sigma 1 fact, and then this is telling you can actually pick the witness for the sigma 1 fact. Okay. All right, so so we prove this theorem. So suppose if you have questions, you should ask, right? Don't worry about stopping me. Okay, so we start with so let A be a subset of power set of omega 1 of r. I guess I should remark that A is really a set of reals, right? So A can be coded by a set of reals. I can just look at set of reals X, for example, look at the prime coordinates, right? Look at the multiples of primes and look at the digits that are indexed on these prime coordinates. There are infinitely many primes, so each real can be split into countably many other reals. Okay, so we now consider the game G star A. And this is the game where 1 and 2 play P0, P1, P2, P3, and etc. And what are the rules? So the rules are I belongs to, there's a finite function from some integer into the real, so it's a finite sequence of reals. And 2 means if and only if the union of the range of AI belongs to A. Okay, so the first question you have to ask is why is this game determined? And that's again the same thing, right? Each finite sequence of reals you can put into one real. So the game is really a game on reals. Let me just make that remark. We can code this game by there is a function, recursive subjection, recursive. Basically. Okay. So
Excuse me, can you
yes,
say again what is after the sum? Is
what
there
is
a
after, what is after
two
what?
wins if and only if?
Two wins if and only if the range of the
Okay.
PI. So PI is a finite function. PI is like
Yeah.
a function from
Thank
some.
you.
Yeah.
So just to check that I've understood the notation correctly, when you say a game on I, you mean a game where each player takes turn to play a single reel?
Yes, because the ADR means that, right?
Okay.
Because ADR means players play reels. They don't play sequences of finite sequences of reels. So why is this game determined? Well, that's because every finite you could just there's an equivalent game where you play reels. Right? Okay, so let's make that the second point B. So ADR implies
Could we make a game with countable, where we don't not play like finite sequences, but countable sequences? Is it equivalent in some sense?
play with countable sequences. Some of the proofs could be you have to. There's a place where you have to start playing catch-ups. I think eventually it will be equivalent, but maybe it's not that easy to.
I mean, countable will be ordered somehow, right? So
Yeah, but you still have to play catch-ups. So if you have countable, you want to close on you want to close under your strategy. So if you have countable sequence, then you have to when you start proving, let's say it's closed on the intersection, then you have to consider all countable subsets of the sequence you played in the first move, and that's continue many. So it's too many basically. With finite, you'll see it will come up. I'll tell you exactly where it comes up. So I think you could start play. You can play a different game. You could play. After knowing that this is the club filter, you'll show that the ultra filter that Solovey defines is really the club filter, and then you can prove that if players play sigma 0, sigma 1, sigma 2, which are countable subsets, and then you require that they cover each other, right? And two keeps covering one's moves, and then 2 wins if the union belongs to the set. That would be equivalent. But anyway, long story short, I don't think it's okay. So now we want to prove what? So A is in mu definition, right? A has measure 1, if and only if 2 wins G star A. 2 wins, that means what? So this means there is a strategy for 2, right? Let's make that remark as well. A strategy two or for 1, right? Is a function tau from finite sequences into finite sequences, right? I guess it's even worse than that. So you'll have finite sequences of finite sequences, right? So basically, a winning strategy, unlike pure AD, for pure AD, the winning strategy is a real, because it's a function from finite sequences of integers into an integer, right? You plug in finite sequences of integers, it gives you an integer back. Here, you plug in finite sequences of the sequence itself consists of finite sequences of reals, and you get another finite sequence of reals. So this is a set of reals. That's also kind of keep in mind that in ADR, the winning strategies are sets of reals. In AD, when you discuss AD, winning strategies are reals. Okay. All right, so what we need to prove three things, right? So I want to see mu is one outer filter. Two, countably complete. Three, fine. This is trivial. And four, normal. And this one is completely trivial, right? All right, let's do three. So peak and a real, right? So want to see that two wins V star A, where A is what? A consists of those sigmas such that the little a belongs to sigma. Okay, so two plays. So what is the algorithm? Let two play the sequence consist. One thing to keep in mind, which is the most important remark about all of this, is that the winning condition depends on the set they produce, not on the sequence. So here you see here it says the union. You take the union of the range. That means the particular order these reals were showing up is not important. What's important is the set at the end. And so just play the A at the beginning and then forget about it, right? So two plays, winning strategy for two. Two plays just this sequence on her first move. That's it. Right? And then it will belong to the whatever set you produce, and so it's a winning strategy. Okay, so let's try one. Now suppose A and A. So suppose A is a subset of P omega 1 alone. And A is not in mu, right? So A is not in mu. What that means is that we want to now show that A complement is in mu. So we want to see that the complement is in mu. And for that, we want to see that the player 2 has a winning strategy, right? We want to see 2 as a winning strategy in GA complement. Okay, so what information do we have? We know that A is not in mu, and we know that every game is determined. So that means player 1 has a winning strategy in the game for A, right? So we have a winning strategy tau for 1 in G star A. 1 wins the game for A. Okay, what that means is that we're gonna play, right? So we're trying to get into A. Remember where 1, if 2 was trying to get into A, that means if 1 follows tau, 1 will get into A complement. Okay, so all 2 has to do is get into, just start playing tau. But tau needs, right? The 2, you need the first move. Tau needs a first, tau doesn't have a first move. I mean, a move before it, right? While 2 always has a move before it. Okay, so what 2 has to do is skip. And now this is where it's important that we looked at the range of the functions, not the order at which the reals appear. Because if we're looking at the range of the functions, 2 can completely ignore 1's first move and just start playing tau. And then start covering 1's moves. Okay, so want to see what does 2 do? So here is the game. 2 plays as follows. Right, so we will have the GA board with the GA complement board. Right, this is the game that 2 is trying to win. And then we have the GA board. And this is the where tau is. Right, so you start out with tau empty here. Okay, so now 1 is playing P0. I need to tell how 2 should respond. Well, 2 ignores. 2 starts playing tau empty. Right, this becomes P1. And now 1 plays P2. What should T2 do? Remember, the goal is to just make sure. What is the goal? The goal is to make sure that whatever you play here, right, the union of the on the second board, the sequences of reals produced in the second board, in the A board, the union is going to be the same as the one you produced on the A complement board. Okay, so it's not that we want to match the order of the reals that they appear. Okay, so what 2 does is puts P0, P2 here, right? And yeah, she already has the empty one. She already has P1, right? This is P1. So she's missing only P0 and P2. And then starts playing, so that would be P3. And then she's just gonna follow tau now, right? And after this, follow tau. Right. So what that means is that if you play P4 here now, she's gonna cover P4 here. Right? She doesn't have to do join anymore. She has all of the reals now that has been played. She already has it, so she's just gonna follow tau. Right. So this is 1 place by tau here. So all of these responses are according to tau. So 2 in G star A complement, 2 follows tau after B3. Let me also draw a line that there are 2 sides, yeah. So what is the
Gregor,
yeah?
is what happens if we don't play finite sequences of reels, but we play just single reels?
I think it works.
It works the same? Because to me, it seems like I can still steal the strategy by just playing always 1 move later. Like you kind of fix the strategy after 1 move already, but you could also just shift the entire application of the strategy 1 move into the future, right? You could just play, and that would work for just sequences of reads. Then you don't have to.
I think it's the same.
Okay, but I thought maybe normality will kind of make this version more handy, or I don't know. Is there a point where we need this version?
Yeah, I could. It's kind of nice that at this step I could just, but I think it works. So
okay,
it's this step I could just right. I could just concatenate the 2 sequences instead of worrying
yeah,
about.
I mean, yeah, you're immediately done. So
yeah.
Okay.
Okay, so that was so why is this working? Why is this a winning strategy? Because want to see that the union of the range of pi belongs to A, but that's because union range pi is produced is according to one's strategy. Right. This is, by the way, an important concept. It's good to, if you're not new to determinacy, you should, especially, I mean, when you have reals, then it's according to tau is, right? If we're keeping the sequences in mind, then according to tau is is more well-defined concept. But here you have to think a little bit. So what does according to tau mean? Imagine I give you a countable set, right? So let me make that remark here. Suppose tau is a strategy. And sigma is in P omega 1 of R, such that sigma is closed under tau.
Rigor, one
Yeah.
quick question. So the fact that mu is closed upwards actually relies on the fact that it's so actually it relies on this fact that either A or AC is in mu, right? Because otherwise it's only obvious from the description of the game that if two wins, then the same strategy wins for a smaller set, but it's not obvious for one, right? That if I can avoid. No, I think it is obvious. Okay. I'm sorry.
Yeah.
No, sorry.
Suppose you have a strategy and you have some countable set of reals. So let's say sigma is closed under tau if any finite sequence you take tau p belongs to sigma, yeah. Yes. Okay. So then, so you want to say if sigma is if if sigma is closed. So look, the sigma is just a set. It's not a sequence of reals, right? If sigma is
Sir, is this remark above a definition of what it means to be closed under, or?
well, I define it now. I'm making a fact. The remark is all of it, right? So if sigma is closed under tau, then sigma can be obtained as the run of the game in which, let's say tau is a player in which, okay, I didn't fix for which player this is a strategy. For player one, right? In which one plays according to, I think just enumerate sigma and let them play and make sure that every real ends up in one of the sequences. So so this is an important thing to keep in mind. All right, so what is next? Next, we want to prove that this is countably closed, right?
Is this? I'm confused. What if sigma is empty? I think you need some assumption. Maybe sigma needs to be one non-empty or
Well,
something.
yes, sigma is not empty.
Or it contains the empty sequence or something like this.
Right, let's say sigma is not empty. Where am I? I need to prove, so I proved fine, I prove ultra, so we need to prove countably complete. Okay, mu is 2, mu is complete. right? So here, this is tricky because you need to pick strategies, and we don't have. I mean, the whole point of the paper is that DC.
I also think, sorry, tau needs to be a strategy for 2 if you just have non-empty, because the element that already is in Sigma, it's not clear that a strategy
Okay, let's
by
say.
1 would go through it. I think.
Okay, so we could say.
Maybe if it's a strategy for player 2, then I think then it works. And
Right, but otherwise, just say empty is in it.
the empty sequences in it, I guess. Sorry, I stopped interrupting.
So why don't we just say empty is in it? What did I write? Where? How am I supposed to? Here. That's that. So mu is countably comparable, which means we have, so pick a I in omega, which is a subset of the omega and log, such that AI belongs to mu. We want to see that the intersection of AI belongs to mu. Right? Okay, let me illustrate how we could do it for 2, and then just sort of hand wave. We do want to see that A, B are in mu. From here we get that A intersection B is in mu. Right? Okay, so A, B in mu means what? So pick tau A and tau B winning strategies for 2 in B star A and B star B. And we want to see that 2 has a winning strategy in G star intersection B. Okay, so we're going to, so what it means, if you have the remark in your mind, what that means is that we have to produce a sigma in this game, right? Which is closed under both tau A and tau B. So idea, play 2 plays so that the sigma they produce, so that the run of the game is closed under both tau A and tau B. So how can you do that? Well, this is right. So we have, okay, so we want to play G A intersection B, and we have our auxiliary boards. These are the auxiliary boards. This is GA star. And this is G, right? 1 and 2. 1. So remember, the payoff depends only on the set they produce, not on the sequence, which means I have to alternate between these 2 boards. Every time I see a new sequence in there, I'll play first here, and then I'll play here in the next move, right? So okay, so 1 and 2 start here. 1 plays P0. What is 2 gonna do? Well, 2 is gonna copy it here and play with tau A P0, which is gonna be my P1. Right? So you're going to put P1 here, then 1 will play P2. What should 2 do now? Well, 2 wants to make sure that whatever they end up playing is the same. The set of reals they produce is the same. Okay, so 2 doesn't, and on the B side, you have nothing yet. Okay, so you take all these 3 things together, you could alternate them, right? And you play them as one's move. And now you have tau's response, two's response. Which is what? This is our P3. This is P3. Okay, so now you get P4. So what should T do now? You take, so what does 2 have here? 2 has P0 and P1. The missing ones are P2, P3, and P4. Okay, so 2 copies these moves here, P2, P3, P4, and then let tau A pick the next move, right? Okay, I mean, it's getting horrendous to write it already. So I'm not going to write it. I'm just going to say P5. So here is the tau. You play according to tau A. Here you play according to tau B, P5. That's it. So keep alternating. Whose strategy, right? Keep alternating. Between the two boards. Okay, that's pretty clear, right? That eventually they will have the same. At each step, if you're in the, okay, so if you're in the A board, so what do? You look at which piece you haven't taken care of yet, and you let one play those. It's usually, it will be 3 of them exactly, the 3 previous ones. And so one plays now exactly those, and then tau gives you a response, and then you move to the next board and look which piece you haven't taken care of. Okay, so you put them all together and you play. So this is easy to digest. And then, okay, how are you gonna do omega many? Well, you're just gonna have omega many. You cannot alternate. The point is that you cannot go the first, the second, the third, the fourth, right? Then you will run out of moves. So what you have to do is use some kind of bookkeeping function, which you play on the first board and move on the second board, and again the first board and the third board and the first board, second board, third board, fourth board, and so you have to use some bookkeeping function, otherwise it will not work, right? Okay, so the general case. So to glue together the strategies, or maybe let's just say the general case. Right. So let the a sequence of winning strategies for AI. So tau I should have said tau B. Okay, tau A is a winning strategy for 2 in this game, right? So 2 plays GA the intersection, so that the one is closed under each tau I. And we can do this by using some kind of we can do this by using a bookkeeping function. Bookkeeping. Does bookkeeping have 2K? Bookkeeping. Yeah. Bookkeeping function, which allows us to return to each board. Infinitely often, right? Infinitely many times. So you have to keep coming back to the same board infinitely times, and each time you come back, you take care of all the moves that you haven't taken care of yet, right? That's the whole point. Okay, so there is something you should be asking, well, how you get the sequence of the strategies, right? It's unclear how you actually pick. If you don't have dependent choice, this is actually the whole point of the Solvay's paper, because you don't have ADR does not imply this. Okay, but you can let so here's the trick that he uses. You let you play an auxiliary, you play a game before you start doing this. So how to get
Gregor, one question though.
yeah.
So how is countable completeness even defined? So I would normally assume that it means if you have a sequence of sets. But strategy is very non-unique. Okay. Okay.
Oh, yeah, that's right.
Is it like
Okay.
we play some kind of choice game before?
Yes, so you play before we do it. We play this game. So one and
It's
two.
similar to one that proves CCR under AD?
Right. So 1 and 2 play the following game. Let's see. 1 plays I, and then 2 plays empty, nothing, right? So 0 doesn't matter really. Let's say 2 plays 0, and then they start playing the game for AI. The rules. I is in omega. P N is in doings. If only if the union of the ranges of PM is in AI. Right, so we had the sequence already. Okay, so it's a game on reals. One of the players has to win, and one cannot win, because if one wins, its move already is known. That's the thing. If one wins, its first move is known. 2 knows what the first move of 1 is. So 2 just picks a strategy for that particular set and plays according to it. Right? Okay, so 1 cannot win this game. Game. So 2 wins, which gives a sequence of the winning strategies, right? Okay. One cannot win because one's move is known. If 1 wins, then one's move is known, and then 2 picks any strategy that works for her, and she just continues playing with that. All right. Okay, so this is completeness. Now normality is pretty much the same thing, just a little bit. What the difference? The difference between normality and countable completeness is just simply that in the case of countable completeness, we know the boards already. Meaning we already see the omega many boards, and we just keep coming back to each one infinitely often. In the game, for normality, you don't see the boards. The boards, you as one makes new moves, you start opening up new boards. That's how it's gonna be. Okay, so just like in the choice context, stationarity is equivalent. I mean, normality is equivalent to diagonal intersection, right? That type of thing. So let's prove that. Mu normal if only if for every x, I mean R indexed family of so I have R indexed family of measure one sets. The set AX, which consists of all those sigmas in here, such that for every x in sigma, sigma belongs to AX. Right? This is a mu. So normality, the function version is equivalent to the diagonal intersection version. Let's prove this. Okay, so let's do this direction, right? So mu is normal. Now we have fix. But it's basically the same proof. And we want to see that that happens, right? So we want to see that this belongs to mu. Okay, so what's going to be our function? Well, pick for each x, we look at, right? So for each x, we look at those. So what is it? AX is in. Want to see the diagonal AX is in mu. So for each sigma, yeah, sorry, for each f of sigma is going to be the set of all x's, right? So let f p omega 1 r into p omega 1 r be given by f of sigma is the set of all x in sigma such that sigma belongs to AX. Right? Yeah. So we have that for every sigma, right? So we have for every sigma, f of sigma is a subset of sigma. So not only measure one, but every. So there exists a particular real such that set of sigma I feel like I'm not proving it right. No, definitely not. There should be sigma is not in A, right? So we have to assume yeah. Suppose not, right? Suppose does not belong to mu. So it's complement belongs to mu, which means what? Which means the set of sigma. So we have that the set of sigma in p omega 1 of r such that there is an X in sigma with the property that sigma does not belong to AX, belongs to mu. And now I need to pick these X's. So now let F from P omega 1 over R into P omega 1 over R is such that what? So I want to say that F of sigma is the set of all X's in sigma with that property, such that sigma does not belong to AX. Right? Which is clearly a subset of sigma. And because the set, right? Because the set is in measure one, we have, I mean, let's call this set B, right? So for a measure one many set, right? Because B is in mu, that the set of sigma in P omega 1 of R such that F of sigma is a subset of sigma belongs to me. Because any sigma in B belongs to yeah. Okay, so now I can pick one X, right? So pick, I guess you want to say F sigma is not empty. I should have said that in the normality. That's the, I didn't say that, right? Here I want F of sigma not to be empty. Otherwise, you cannot find such an A. So the set we care about is really F of sigma is a, here I should say F of sigma is a subset of sigma, and F of sigma is not empty. The way I define F of sigma, it's always subset of sigma, but it could be empty. So this is in mu. This is in mu because any sigma in B is in this set. Okay, so now pick by the because mu is normal, right? According to definition. So pick A in R such that the set of sigma with A in F sigma is in mu. So this means what? But instead of sigma such that A is in F sigma consists of what? Set of sigma such that sigma does not belong to A and A is in sigma. But it's fine. So this is measure one. But from here it follows that A is not in mu. Right? Because if it was in mu, this, if I mean, from here it follows that, yeah. From here it follows that A complement is in mu because the set of sigma which belong to it will be, and then you have that. Okay, so the other direction when you have this from to the function, that's easier, yes. So this direction goes we have F such that the set of sigma F sigma is not empty and Okay. Sigma is a subset of sigma that belongs to mu. Okay, now we want to get an A, right? So if we want to see that there exists a real such that the set of sigma with A F sigma is in mu. Okay, and now what we do is we look at for each, assume there is no such real, then for each A, look at all those sigmas for which A is not in F of sigma, and then use diagonal intersection, right? Assume not, and for A in R, let this be the set of all sigmas such that A is not in F sigma. Right, so this measure one. So for every A, we have for every A in R, A has measure one, because for no A this is supposed to happen. Okay, but then we have the diagonal intersection is in measure one. So we have that the diagonal AA is measure one, for which you get that the set of sigma such that for every A in sigma, sigma belongs to A is measure one. But then if I pick a sigma like this, I'll get into trouble, right? I'll pick sigma such in here, such that for every A in sigma, sigma belongs to AA, then it cannot belong to any of them. Sorry, then F of sigma cannot be inside sigma. Then F of sigma is not a subset of sigma. That's a contradiction, right? Because we assume that there on measure one many sigmas, F of sigma is a subset of sigma. But if I pick a sigma in this measure one set, F of sigma is not a subset of sigma. Contradiction. Okay. So this is gonna we'll prove this version of normality, right? So back to this always term. Okay, want to see that normality, which means now I want to apply. Okay, so we have our indexed collection of measure one sets. So this is R indexed. And now I want to argue that the diagonal intersection belongs to me, right? So I want to see that the diagonal intersection belongs to mu. Okay, so what is it that we want to do? What this means, if you remember that remark about closure points, I have strategies for each AX. Player one has a strategy for each AX. And now you want to produce a strategy such that if in this game, right, that means every time you have a run of that game, it has to be closed under all the strategies for the reals that are in your sigma. So fix is a winning strategy for true in AX. Again, we have to somehow pick the strategies, but it's the same trick like we did before. Want to find winning strategy for 2 in G symmetric AX star. And so how are we going to do it? Well, 2's goal is to, so idea, and you know, if you have to think about this idea, it's actually, I cannot write it down, it will take forever, but it's just like the countable completeness. And the idea is basically to place in such a way that if sigma is a run, then for any x I pick from sigma, sigma is closed on the tau x. Right? So what does this mean? One is going to play, right? So one starts playing in the G star in this game. Okay, so one produced some reals. Okay. You already see the reals, so you already know which strategies you have to pick. Right? And now you're going to make sure that you come back to those boards infinitely often. Okay, so and you pick the first board and you respond as your 2. That's your 2. That's the 2's response. Okay, then one is going to open up more reals. That means now you open up new boards. And then you make sure that you're going to come back to those boards infinitely often. Right? So how does this game proceed? You have 1, 2. 1 place P0, so what is here? Okay, but P0 is what? Right? So P0 is going to be some sequence, x0, x1, x, and 0. This means that I have to open up all of these boards. Right? So this is first move. Okay, so open all of these boards. G, A, x0. Right, so here you're going to play according to tau x0. Then you have G, A, x1, the stars, sorry. So here we're going to play with tau x1 and so on. G star, A, x, and 0, and we're going to play tau x 0. All right, so then there's 1 and 2. And we're going to let that be P0 and this be P1. Right, so P1 is here. And then you take that and move here. Right? All right. So let P1 here. Okay, then 2 is going to play. 1 is going to respond with P2. What do we do next? Well, P2 is going to force us to open up more moves. Right? So P2 is, I guess even P1 is going to force us to play new boards. So it's not just P2, but we're going to have P1 followed by P2 is equal to, oh, maybe I should put zeros here. Right, so here is going to be x 1, 0, x 1, 1, x 1 and 1. And so open all of these boards. And then, right? Okay, so then play P2, P3. maybe it comes one of your boards. Maybe it comes from here, and etc. And so the description is as one and two play more reels, two open small boards. Right, so you have to open up more boards, and then the idea is that you will keep coming back infinitely often. Then two needs to come back to each of these boards. Right. And this is the step when if you had infinitely many reels, then you have to have, in each step, you have to open infinitely many boards. Continue many boards. But here in each step, you open only finitely many boards and you have countably many moves. You can take care of it. So this works. Just like in the case of countable. Yeah. All right. So, but then there is one remaining question. How did I get the strategies?
So may I ask?
Yeah.
When we choose these strategies, we don't like choose strategies. It's like we choose rather like we cannot choose the whole strategy, right?
Yeah. No, we have to again play like we did in the countable case.
It's like, yeah.
Well, why can you not choose whole strategy? I mean, what do you mean?
Well, we cannot make our many. We don't have DCR, so you don't have.
But the same. I mean, the same proof that let us choose
Yes, it's the
countably
same
many.
proof. I'm gonna do the same.
But
I
even
mean, the proof you gave just showed that you can make. You have choice of sets of sequences, sets of strategies.
maybe I don't see something, but it's not like we can choose these strategies. It's
But we are
rather
letting-
we
we're letting-
find a way to, we can choose a ways to play according to our needs, right? And
Can
No, I
let-
mean the strategy for the disjoint union is just you have like an R disjoint union of copies of R, and I mean just what Gregor did for the countable many strategies. And then the strategy for this game is a choice function.
Can I do it? Or, so what we do is we just
yeah,
we're
yeah,
not gonna
go on.
choose them. We're just gonna play a game that does it for us, right? So player one is playing a real x 0, 2 plays 0, and then they start playing p0, p1, p2, p3, and etc. Then the rules are so x0 is a real, and pi belongs to our finite sequence, and 2 wins if and only if the union of, so the set they produce, but only pi's, we don't care about x, belongs to a x0, right? Okay, so now one cannot win again. We know by ADR. So by ADR, game is determined. So one of the players has a winning strategy. But one cannot win. Right? Because if one wins, then her first move is known. So 2 just picks any strategy that works for AX0 and keeps playing with that. So 1 cannot win, which means 2 wins. So 2 wins. But what is the winning strategy now? So let F be a winning strategy for 2. But this winning strategy is what? 1 can play any real, and then after that, this winning strategy, right? So you can think of, so F, so if X is a real, then Fx, which is given by concatenating with X, right? Fx is a winning strategy for 2 in AX. And what is Fx? Where Fx is what you plug in a, say, P0, P1, P2, P2, and it's giving you back X followed by 0, followed by P0, followed by P1, followed by P2. Right. So this is how you choose it. You could use some other ways. So you, for example, Maskovakis has like a theorem that says the strategies will be simply definable from the game, and they could use things, more complicated things like that. But this is very cool trick.
I mean, I have a suggestion for the main proof here. Could you not do a similar argument, like applying ADR again for the normality proof? So to avoid to thinking of opening up new boards over and over. I thought maybe, but maybe not. Maybe I'm confused. Like you look at the complement, you assume somehow that it's not winning for player. What do we want, player 2, and then you show that you have a way to play against player 1's supposed winning strategy. But maybe,
Yeah, but then
maybe that's not.
how we again open up games, right? You should. It will again probably will be the dual of whatever I did here.
Maybe it's not really. Yeah. I mean, it somehow spares you this bookkeeping function, because the supposed winning strategy for player 1, like here you're using again some kind of bookkeeping, right, to keep track which X's have already been played, and then you use those to figure out which X's play later. It's very hard to think about, maybe for some people. and the other way around, you have the strategy for player 1, so you already know what's being played in each branch, right?
Yeah, but
So
but you have to pick 2 moves now.
yeah, you're right. It comes down to the same. You're right. Okay.
By the way, about this main proof, because I thought a bit about this, I was also not sure after previous session. I have another hint, like a suggestion how it may be easier formalized, that so that maybe we don't have to like open because when the new move produces new finitely many reals, maybe we don't have to like open all of them, all of the new boards at once. We may open only one new board at once.
Okay.
But eventually, because we are producing countable sets, eventually all of the boards will be opened. But at once, we may open only one new board.
Yeah, then you would need a simpler pairing
I think
function.
now then it produces more similar situation to this omega 1 completeness proof.
Yeah.
This is also, I think, the idea to when you don't want to play sequences of reels, but just single reels. This is also the idea why everything works, right? Because yeah, the same trick that you only open, you only need one reel, and after infinitely many turns, you will have taken off care of, like you will catch your tail, kind of the same catching your tail idea.
Yeah. Okay, so we have 10 minutes. What should I do? I guess we continue next time. What I mean, in the email I said you don't need any. So for me, ADs, you need basic things from AD, but I mean they are deep theorems. It depends on what perspective you look at it. So for example, we need the following theorem. So let me just give you like a few theorems that we need, and then you tell me if you would like to see a proof. Theorems we need. Right, remember the goal is to get omega 1 dense ideal. Yeah.
I have another suggestion in the same direction, because Jan asked if we can play for countably many. It seems that this also works, maybe, except I don't quite. I think
But
the
you
same.
have to game. You have to say you play the covering game where player 2 covers the moves of the player 1 and gets into your set, and then you say you want to make sure that the union gets into the set. So it's a different type of game, and 2 can win that game.
Okay.
So you can say 1 wins. I mean, your set is in the as measure 1 if 2 wins this game, and then I think the measure you produce will be the same because this is the club filter. So it's like there are clubs. All right, so let's see. I mean, you guys can discuss. This is a really great theorem. There are lots of questions. I'm not sure if any of them are open these days. But there was a question about the uniqueness of this measure, which now I'm trying to resolve, I think, with some. Anyway, it's an interesting topic. Okay, but for the dense ideal proof, we need some basic determinacy facts, and here is one. Let me give you a definition. So this is the theta, which is the supremum of alpha that exists f from the reals. Okay. Alpha f is onto, so it's a surjection. Okay, so there is Moskowakis coding the coding lemma, but we don't need the full force of coding lemma. I think maybe we need I think this version was actually due to Harvey Friedman. So this is the easy version. Let's call it baby version. The easy version. The simple version. So it says if alpha is less than theta, then there exists f. Okay, so if alpha is less than theta, that means there's a surjection of reals onto alpha. But even more, there is a surjection of reals onto power set of alpha. F is on. Moskowakis, the coding lemma says this surjection is kind of simple. So if you give me a surjection onto Right, there's an interesting question here. How complicated is the surjection of reals onto power set of alpha given if I give you a surjection onto alpha, could you cook up one onto power set of alpha? And turns out it's quite easily definable from a surjection of reals onto alpha. So Masquerades proves much more complicated theorem. But this is yeah, this is I think in Kanamori. Proof. The full theorem Masquerades is calling them is in Masquerades' book and probably in the Cabals. So we need this. Another thing we need is wage lemma. So this is easy. Oh, I mean assume AT, yeah. Okay, so this is called wage lemma. So basically saying either A is wage reducible to B or B is wage reducible to A complement. So either assume AT. Either then for any AB either A is wage reducible to B or B is wage reducible to A complement, and here this is continuous to image. There is a function. Remember, reals is the bare space, right? Continuous such that A equals F inverse B. And this is not too hard. Let me give you the proof, just sort of outline. First, winning strategies for the ordinary games are continuous functions. They're Lipschitz functions, right? So consider the game. So let's call it GAB game. So what does this game do? They play independently. And then, so the rules are, of course, these are integers. And I and mi belongs to omega. And one wins if only if the real x is in A, then if only y is in B. So where x is the n0, n1, and y is y0, y1, yi. Okay, so you could check that if one wins, then you would reduce what? Then you would reduce A to B, because the winning strategies are Lipschitz functions. They generate continuous functions, right? Because why is it continuous? Because it's telling you how to basically from finite sequence how to construct the next sequence. So use your continuous function. So that means so if one wins, that means if I take a Y in B and I pull back by the winning strategy, then I would get into A, right? If 2 wins, is the other way. That means if I take something in the complement of A and pull back, I will get into B. So if 1 wins, you get A is reducible to B. If 2 wins, then you get B is wedge reducible to A complement. Right? Just basic analysis of what happens. The truly important theorem is Martin's theorem. And Martin proved assume AD. And for then is well founded. So this is an extremely important theorem. It's used a lot. I don't know if you want to see the proof. Another theorem which you can really prove, we can do it as a homework. It's well founded. What is its length? You can prove its data. So another thing that we will use is Wooden's theorem.
You have 10 seconds, I think.
Well, it will keep going. It will not
Oh,
kick you out.
I was
but it's okay.
thinking-
I will finish. This is the last thing I will write. So Wooden's theorem, which we will need, is that there is a unique assume ADR. I think it's just assume AD. Yeah, assume ADR. Then for every X such that there exists a surjection, right? This is that's the symbol for surjection. There is a unique, for every X with this property, there is a unique non-line ultrafilter. I was thinking of doing this next time. One direction is very easy because if reals can surject onto X, we will just take Solovey's measure and push it by this F, right? So the existence is very easy. Is the other direction, so show that that's the only one. What's going to be very what is a little bit hard to prove. Okay, so send me an email if you want to see any of these. We could spend the day one time doing whichever one you want. Okay, so see you next time, guys. Unless you have questions, is there any question? No? Then I guess see you next time, yes?
Yeah.
Oh, remember, next week, no seminar next week. I have to do the week after. All right. Ciao, guys.
Thanks.
Thank you.
Bye.
Bye.
Thank you.
Thank you.
Bye.
Bye-bye.